Now we're going to check out how to find the percent composition of a compound. If we take a look at the model here, the dark ones are carbon, the small ones are hydrogen, and the red one is oxygen. This is actually a molecule of ethyl alcohol. Now you really can't tell that by the formula C2H6O, but we can tell by looking at that model of it. Alright, so how do we find the percent composition? This was something that people could do many years ago without even having formulas. So, percent by mass of each element in a compound would be a definition for percent composition. So in order to find percent composition, we need to have the molar mass, number one. So once I have the molar mass, I can take the mass that the element is contributing to it, multiply it by 100, and then divide by that molar mass, and I'll get my answer. So the molar mass for ethyl alcohol, if I figure that out, that would be 46. So what about for the carbon? Well, carbon is contributing 24 out of the 46. So there's 24 times 100 over 46, 52.2%. So make sure you don't just put the atomic mass of the element on top. It's whatever that element is contributing to the total mass. For hydrogen, it would be 13%. For oxygen, 34.8%. And this was something that was very handy to use once you knew it. Years ago, when people were concerned with making iron, they would find making steel, they needed iron for that. You find iron in the ground in different ores, and they would want to know how much iron do they expect to get out of these ores. And the simplest thing to use would be a percentage. Why don't you try this one here? Find the percent composition of acetaminophen, that's the painkiller in Tylenol. So why don't you pause now, try that, and then come back and see the solution to it. Okay, the solution to this problem, we're going to take the formula and figure out the molar mass. So it's 8 times 12 for carbon, plus 9 times 1 for hydrogen, plus 14, plus 2 times 16 for the oxygen, and I get 151 total. So, for the carbon, it's going to be 63.6%, hydrogen 6%, nitrogen 9.3%, and oxygen 21.2%. Again, I like to keep a number in the tens place for this. When you finish, your percentages should pretty much add up to 100. Sometimes because of rounding, you might get 99.9, but that's one way to know that you did it correctly. Now, something that we saw in Chapter 2, we're going to bring out again. That's the difference between molecular formulas and empirical formulas. Because people could find the empirical formula many, many years ago. They knew that it wasn't necessarily the true formula, because as we saw, more than one compound can have the same empirical formula. So now I'm going to go through, and this will be the last topic in this session. How do you find the empirical formula in the lab? You'll be doing that in one of the experiments. And then how do we find the molecular formula? What do we need to know? So from Chapter 2, we made up a couple of columns with molecular and empirical formulas. You notice that water is both molecular and empirical because it's the simplest ratio, which means it's empirical. And it also represents a substance as it exists in nature. Here's glucose. That's a molecular formula. We can tell right away because these numbers are reducible. And this is its empirical formula. Now, more than one compound has that same empirical formula. You notice it's the same for this compound, dinitrogen tetrahydride. Its molecular formula is smaller. Now, these are the only kind of formulas that people could come up with years ago. They were lacking the true molar mass. We're going to see that as we go on. So how can we find the empirical formula in the laboratory? Well, this is one way to do it. We would break the compound down into its elements if we started with the compound. Determine the mass of each element. Now, we also could do the opposite. If we just started with the elements, we could determine their masses and then make the compound. Either direction works. We convert the masses of the elements to moles, and then we're going to reduce the number of moles to a simple whole number ratio. And that whole number ratio are going to be our subscripts. So here's an example. We have an unknown compound, and we have the masses of the elements that were found. 15.3 grams of sodium, 4 grams of carbon, 16 grams of oxygen. I do want to mention that if they gave you the percentages instead of grams, that would be just as fine. We would just drop the percent sign and replace it with grams, because percent just means out of 100. So either one works. All right, so the first thing to do is convert grams to moles for each element. So we need to look up the atomic masses. So the atomic mass of sodium is 23. If I take the mass from the problem and divide it by 23, I get 0.665 moles of sodium. For carbon, 4 grams is 1 mole is 12 grams, 0.33 moles. And lastly, for the oxygen, 1 mole. All right, so I have my numbers of moles. Now the next step would be to reduce these three numbers to a simple whole number ratio. And to do that, I'm going to take the smallest of the three number of moles, which is 0.333, divide it into itself and into the other two numbers of moles. And when I do that, see what I get for an answer. I get 1 for the carbon, 2 for the sodium, and 3 for the oxygen. Therefore, my formula, Na2CO3. You might recognize CO3 as carbonate. So this is sodium carbonate. Now, sometimes you don't get all whole numbers like this, and I'll show you in class what we do when we come up with maybe 2.5 to 1 to 3. What do we do then? So don't worry about that for now. All right, here's another one for you to try. You notice now we're given the percentages rather than masses. So we can just drop the percentages, replace them with grams, and then do the same thing you did before. So what's the empirical formula for the compound? So we're going to take our masses of each element, convert it to moles, and then reduce. So why don't you stop at this point, give it a try, and then come back and see the solution. Okay, here's the solution. So to get my numbers of moles of carbon, it's the mass of carbon divided by 12. The nitrogen, the mass divided by its atomic mass, 14. Hydrogen, and the oxygen. So that was my first step, getting the number of moles. Now when I look at my numbers of moles, the smallest number is this 0.884. I see it's appearing twice. So I'm going to divide my 4 numbers of moles by 0.884. I always divide by the smallest. And when I do that, look what my ratio becomes. So therefore, I'm going to get the formula, C6N-H17O. Now you might not be sure of how to write this, what order, but it's almost always the carbon first and the oxygen last. Everything else kind of goes in the middle. So that's an empirical formula. Now let's go through one more, and this is a simple one. I have my carbon and hydrogen. You have the percentages. Now see if you can find the empirical formula. Okay, so this is what we would do then. I'm going to replace percent with grams, find the number of moles of each. Straightforward. You notice the number of moles are the same. So when I reduce this, I'm going to get an answer of CH for the empirical formula. Now what if I have that CH, and now I want the true molar mass? Given the true molar mass is 78. Now this is something people could find later without ever knowing what the compound is. Kind of do that in Chem 2. But can I get the molecular formula if I know the empirical and know the true molar mass? And the answer is yeah. So, first thing I want to do is find the molar mass using the empirical formula. So the empirical formula is CH, so the molar mass comes out to be 13. I'm going to divide the true molar mass, which was 78, by the molar mass from the empirical formula, which is 13. When I do that, I get an answer of 6. What this tells me is that the true formula must be 6 times bigger than the empirical, since the molar masses are in that same ratio. So therefore, the true formula is this times 6, or C6H6. Now should I leave it like this? No, I really want to distribute that 6 across the formula. So C6H6 then is the molecular formula. So after people found out a way to get these molecular masses, these true molar masses, then they could come up with the true formulas. Now what about after that point? Well, what if we already had the true molar mass and We want to find the let's say not the empirical formula, but let's say we have the percentages maybe. Can we figure out the molecular formula without having to get the empirical? And the answer is yeah. Let's try one like that. So here we have an unknown compound, and its percentage is broken down like that. And we have the true molar mass. Now there are machines today that can give you this. There's a machine called the mass spectrometer, which can give you the true molar mass of a compound, without ever knowing what the compound is. Now let's say we have the percentages. Could I find its molecular formula in a straightforward fashion? Well, I can. Because what I can do is take this 168 grams and say, you know, out of this total mass, 57.1% of that mass is carbon, 4.8% of that mass is hydrogen, 38.1% of that mass is sulfur. Then we go from mass to moles, and I'm home. So let's see. I take my 168 grams, my true molar mass, multiply it by 57.1%. Remember, that's 0.571, and I get this many grams of carbon. I do the same for the other elements. I multiply that same total, that true molar mass, by the percentage. In fact, if you add up these masses, you should wind up with 168. And we're going to change each of these three masses to moles by dividing by their atomic masses. And I get 8, 8, and 2. So therefore, my true formula is C8H8S2. What would the empirical formula be? Well, all I have to do is just reduce these numbers, and I would get the empirical formula of C4H4S. So you see, there's more than one way to do this. Okay, and that's the end of the show.